Hi everyone. Good morning, good afternoon, good evening. I am Shravan Pagroth and I am a simulation consultant at SimWell. I have my background in mechanical engineering and with me today is Stephen Downing, an operations engineer at BlueScope Steels. Stephen has over 20 years of experience working with metallurgical processes and operations engineering. Today we'll be presenting the work we did with BlueScope Steel, the largest steel manufacturer in Australia at the largest site in Port Kembla. We worked with BlueScope to model the impact of new additions they were making to the site. Before diving in, I would like to sketch out the structure of the presentation. Stephen will first guide you through the high-level process of the slab yard that has been modeled as well as the challenges in the process. Then we will go through why a simulation-based approach was used and why specifically AnyLogic was deemed fit for the task. After that, we'll delve into the modeling bits and finally the methods used for confirming that the model was an adequate representation of real life process and the results and benefits it's provided to scope with. And with this, I would like to hand over to Stephen to continue.
Thank you very much, Siobhan. As Siobhan said, my name's Stephen Downing. It's wonderful here to be beginning the conference today, and I'd like to thank Ryan from AnyLogic for being such a wonderful host. I'd like to just begin with a short acknowledgement of country. I'm speaking to you today from Port Kembla, which is a part of the city of Wollongong, about an hour's drive down the coast south of Sydney. Here we live and work in Dharawal country on the lands of the Wadi Wadi people, to whom I'd like to pay my respects and acknowledge elders past, present, and emerging. So here in Port Kembla, we are now actually celebrating 99 years of making steel on this site. We've had many names over those years, but for more than 20 of those, we've been BlueScope. BlueScope Steel is what we'd call a traditional integrated steelworks. If we go to the next slide, so that means we actually take locally sourced coal that's mined in the right on our doorstep. We can pass that through our coke ovens to turn the coal into coke. We take Australian iron ore, and convert that into sinter and charge them both into a blast furnace. That blast furnace creates molten iron, which is high in impurities. So we take that molten iron and run that through a basic oxygen steel converter to purify that, convert it to steel, from whence we then add alloys to our customer requirements, and that steel is then cast through a continuous casting machine into large slabs. Those slabs are then moved to a large warehousing processing area we call the slab yard. And from there, that slab yard then takes those slabs and puts them into one of our two hot rolling processes. Here in Port Kembla, we have a large hot strip mill making coiled products and a significant plate mill. So today's investigation is around our plate mill operations and how the interactions occur between a large project in the plate mill and the slab yard. So we continue. So the plate mill in Port Kembla is over 63 years old. So as a process over the years, we're quite proud that we've been able to keep up with changing technologies as best we can. But there are definitely some legacy items that's very difficult. So of them that have been very difficult to replace is our existing reheat furnaces. So they are the original reheat furnace. So that's here on the left, we see the purple and green structures in that small image. I form part of a project that is looking to modernize our plate mill operations, and the major part of that, over $300 million investment, the lion's share of that is going towards a large walking beam reheat furnace. You can see here the red structure. So of note, that structure is actually quite a bit longer, and being longer than the existing furnaces, it enables us to have greater throughput, have greater efficiencies, and particularly have a lower carbon footprint per ton of steel that we produce. You see on the right here, this is the original operations layout. You can see a warehouse full of slabs that are waiting and to be charged into our furnace. And when I say charged, that's just a term to say that we are putting the slab inside the furnace, which you can see the table there on the right in the background where the slabs will get placed. So if we could continue on, this introduction of a very large new structure in this warehousing processing facility straight away threw up some concerns around the impact on their operations. We were going to increase demand, so throughput through that yard was going to significantly increase with increasing demand in the local market, as well as increasing capacity from the new furnace. And it was also going to have the corresponding effect of reducing the storage that they had to work with. So it was going to make things difficult on two fronts for the slab yard. We keep going. You can see here on the right there, that was the images of the slab yard. But as a basic representation, you can see here some excerpts from the modeling that was done. The yellow dots represent all the storage locations, with the grey squares being the slabs, which will be stacked multiple up to 3 meters in height. You can see there we go from a fairly straightforward operations with not too many obstacles to, on the right, we see the projected state where a large amount of those spaces are now gone, occupied by the new structure. And we've had to introduce these red blocks, which represent some of the old and certainly lots of the new structure, which the cranes cannot pass over. So it makes it much more difficult. The length of travel and time to provide slabs to our furnaces will be greatly increased. So the problem was straight away complex. It may be, some people might say, just a warehouse, but there's a lot of inventory management, processing of our slabs occurring. For instance, our slabs actually arrive as 12-meter slabs, and they have to be subdivided down to approximately 2.5 to 3 meters to be able to be entered into our process at the plate mill. We knew we were going to have to meet this challenge, but our project was also well underway. So we established a multi-million-dollar contingency fund in excess of tens of millions of dollars, without an actual clear picture of what the solution would be, but also not exactly a clear picture of the problem. So we needed to set out with an approach that could both qualify and quantify the problem that would be created in the slab yard processes, and to understand how that might threaten our overall business case and what the solutions might look like. So to summarize some of the key points of those challenges is, as I've mentioned, the increase in production, throughput, volume through the yards, as you would call it, the loss of the storage space, so making that increase even more difficult to deal with. The modeling of the cranes is essential to this process. So as a warehouse, the cranes are the lifeblood of that. And we have very close controlled interactions, which previous modeling of other cranes processes has revealed to us, like in other projects, that would be going to be a difficult and not a simple item to model. Then as well, there's the priority tasking of those cranes. So as in, it needs to be dynamic. So those chain priority, one moment might be one way and then need to be overwritten to a different priority as the emerging process changes. Due to the restriction, or particularly during the construction phase, there was a number of areas that the cranes had to be forced to avoid to keep people safe, and also to keep equipment from being destroyed potentially if a slab was to drop. And then there's, of course, managing modeling and managing the transfer car, as there is 2 yards in this setup. So we need to manage the inventory between both of those and the space that the slabs occupy. And I've mentioned before, modeling of the slab cutting process, which is essentially a process within the process that needed to have its own representative structure. As we continue, so by simulation. It's going to be very clear. It came very clear to us very quickly that there was no spreadsheet exercise that was going to lay out our problem and give us the granularity or understanding of what we needed. We needed a detailed, complex process modeling. The range of requirements, the rates, the competing rates between our rolling process versus the heating process that was required, versus the throughput through our cutting, our inventory management, versus completely seemingly disconnected process of how the slabs enter the yard. All of that just couldn't be made up from artificial schedules. Then you add on top of that the imperative need to have real life crane behavior in those models to achieve the efficiencies that we would need and what we actually do achieve. And yeah, the complexities of running that schedule, all those different separate schedules from start to finish in the process, and keeping that all balanced along with our inventory, not exceeding any limits or depleting in different areas. Hence, a simulation was the only way forward. And so AnyLogic has long been the software of choice in BlueScope. In fact, it was the only processing simulation software that we will allow any of our areas to engage with. So that led to us engaging with SimWell, a great fit for us, a natural choice for their experience with AnyLogic and their ability to deliver on and meet the complex requirements that we had. So I'll pass that back to Siobhan. Thank you.
Thanks a lot, Stephen, for the beautiful introduction. And other than the familiarity and experience SimWell has with AnyLogic, there were a lot of technical advantages that AnyLogic would have provided us with in context of this project. The model needed custom agents, as Stephen explained, to adequately represent the complexity and interaction between the cranes and other equipments in the slab yard. With the added ability to combine benefits of agent-to-agent communication, of agent-based modeling, and discrete-event modeling, AnyLogic proved to be a tool that made this complex interaction smoother to implement. As it is a code-based environment as well, with the added ability to modularize the code components to further build upon, it was a no-brainer to go ahead with AnyLogic, as we were going to do further scenarios to build upon. And now let's get into the technical bits of the model. There are two yards in the process, the upper yard and the lower yard, and they are connected via a transfer car that you see in the middle. All slabs enter the slab yard process via the upper yard on a group of wagons, or as they are referred to henceforth, rakes. These slabs are moved to a stack location via the upper yard crane. The location of movement is based on a multitude of factors. The length of the slab determines the grid position where the slab will be moved to, ensuring that we are efficiently using the space in the yard. The stacking of slabs is determined by the maximum stack height, the dimensions of the slab, and there are overhang constraints as well, which define how much a slab can kind of stick out beyond a particular limit. The upper yard crane moves the slabs from rakes to the yard, as well as from the yard to the transfer car, and from the transfer car to the yard as the transfer is required. And going deeper into the rakes, so basically the slabs come into the upper yard on rakes, as I mentioned. And when a rake comes in, a request is sent to the cranes, and depending on what the crane is doing at the time, it determines the priority of the tasks, and it starts unloading wagon one at a time. So basically, you'll see slabs have arrived on these yellow wagons, and these blue ones are the slabs, and you'll see that the crane is moving to unload the wagons. And lower yard is basically where the bulk of the slab movement and processing happens. Bigger slabs enter from the upper yard through the transfer car. So from here, they enter the lower yard, and these slabs then move into the slab cutter on the bottom right here, where they are subdivided into smaller slabs as per requirement. The movement of all of these slabs is based on a fixed sequence that needs to be charged into the furnace over here, which drives the slabs being cut and transported. After being cut, they are transported to an assembly area. So after the cutting here, they are transported here into the assembly area, and after which they are transported to the charging area. As Stephen mentioned, charging is the process of putting the slabs in the furnace to simplify it a bit. And this charging is being done by the lift crane that you see over here, which is a magnet crane, so it can only pick up one slab at a time, while the right crane that you see over here is a tongue crane, so it can pick up multiple slabs at a time. So we try to bring in multiple slabs into the charging area, but we need to make sure that they're in the correct sequence. So the top slab is the next required in the furnace, so that we're not asking the left crane, which can only pick one at a time, to do digging and find the slab that it needs to. It's just always available to it on the top. The transfer car is another important component which handles movement between the slabs, and as it is a single shared resource between the yards, it is necessary to model the working and utilization of the transfer car correctly. The transfer car operates on two layers of priority. When a task comes in, it is put in a queue ordered by the priority of the task inside the transfer car, and when a transfer car picks up a task according to the priority, the yard where the transfer car is prioritizes the task to supply to the transfer car. So here you'll see the transfer car is in the upper yard and it wants a slab. So the crane brings in a slab. That slab moves to the lower yard, and then the right crane in the lower yard basically prioritizes moving out the slab from the transfer car so that we can have the transfer car free as quickly as possible. The slab cutter, as Stephen explained, is a process inside the process. So it's an operation within the operation, sort of, where it has a cutter with two beds. So here you'll see that we have two beds over here. And there is also a crane that moves inside this compound, which is marked by the blue rectangles, to load and unload the main cutting process. The crane movements have not been modeled physically, but as a mathematical calculation of the movement time, because there were a lot of manual processes and interactions there. So it was decided that it was better to model it as a mathematical calculation of the time. And here you'll see that a slab is loaded onto the right cutting bed. So you'll see a slab magically appear, which is the mathematical calculation. And then it is subdivided as the slabs on the left side are already been done. And then these will be unloaded, as you can see, on the compound area, after which the right crane in the lower yard will pick it up and move it to the assembly area. The crane being an important part of the slab yard, it had to have a bunch of custom movement patterns to it. Hence, a from scratch approach was used to model it. And it was decided that it would be hierarchical in nature, where we'll have a base agent and we'll build on top of it. And here we have basically a crane base agent, then we have the crane bridge, a crane trolley, and a crane hoist on top of it, which have their own movements. So crane bridge will move in the x-axis, crane trolley moves in the y-axis inside the bridge, and then the hoist moves z-axis to kind of pick up the slab, which will be better explained in this video. Here you'll see that the crane needs to put a slab somewhere. So first it positions itself over the stack where it needs to put the slab into, and then it first moved its X, which is the crane bridge, which is the yellow part you see here, then the trolley, which is the brown rectangle that you see, and then the hoist will be lowered to put the slab into the stack it needs to. And as the cranes have to do a variety of tasks, as Steven said, it is important that the crane pick up the task that is correct, so that we are ensuring efficient supply of slabs to the furnace and thus efficient working of the slab yard. The crane used an input table to determine which task to prioritize. Here in the video, what you'll see is that is the same example of a transfer task has come in, and as it is important that we prioritize this task, the crane will basically, after it's done with its earlier task, it will prioritize this task over anything else. And what you'll also see in the video is an example of crane shadowing or crane interaction, where the right crane has to move in to supply slabs into the charging area, for which it will ask the left crane to move out of its way. So right now it has asked crane 8 to move out of the left crane to move out of its way. And similarly, because the left crane will have to now charge slabs into the furnace, it will ask the right crane to move out of its way, as you can see over here. And as it goes further out, it again asks the crane to move out of its way so that it's able to charge. Another important bit was during the construction phase, there were areas that were restricted to cranes as we don't want slabs to be transferred over equipment or workers. To accommodate for this, restricted areas were created, which are here marked in red, and it was made sure that the cranes take a path which is avoiding these restricted areas, but at the same time efficient enough so that we're not uh, causing issues. So here you'll see the left crane has to pick up a slab over here. So it basically moves out of the way of the restricted area, picks up the slab, and then moves back. So these and this is the last screen bit, which is the digging out of slabs, which is another important part. It is necessary to supply the slabs in required order to the furnace and charging area, as I explained earlier. And often to access the required slabs, they need to be dug out from the stack. So we need to remove the top few slabs to get to the slab that we need to. And we also make sure that we're not only supplying one slab to the charging area, we try to supply a bunch of slabs depending on, how easy it is to dig out those slabs from underneath the slabs they are buried by. And then these are moved. And model implements this digging out of slabs and also looks for the next slabs, as I said, that can be transferred over at once in sequence to efficiently use the crane. Here we see an example where basically the required order was in the reverse. So the slabs in green right now are in the reverse order of what they need to be in to be supplied to the furnace. And here you'll see, this is an extreme example, but here you'll see that the crane basically separates them out and then picks them up in the reverse order to make sure that we're supplying in the correct order. Yeah, so here we have started picking them up in the reverse order. And then these will be moved out to wherever they need to be. So yeah, it was quite interesting modeling all of this. And another thing was after the crane and slab yard operations, the slabs from the charging area are charged into a furnace, where the main change of operation occurs between scenarios because we have a new furnace there. We have modeled three main modes of operation for the furnace: the single and dual pusher furnace, which is the current operation. And during the construction phase, this is the operation that will remain. And the walking beam furnace, which is the future state of operations. And after the furnace, the slabs are moved into a rolling mill. And rolling of slabs is a multiple step process, with each process taking a different amount of time for different slabs. And to make sure that there aren't any slabs that are waiting on the process steps and there is efficient throughput of slabs out of the rolling mill, a pacing logic was developed to ensure that the model will have the correct demand from slab, yard, and furnace. Going a bit deeper into the furnace operation, the model operation is quite different for the two furnaces. For the single pusher furnace, we see that a single slab will be pushed into the furnace, and that prompts it to push out a slab to go into the rolling mill, which is the bit that you see over here. So this is the rolling mill, and this is the furnace. While if we look at the walking beam furnace, we see that it's a longer furnace, 30% longer in fact, and then we charge in the slabs two at a time, and then they are released as a as I said, there is a pacing logic that asks the furnace to give out the slab when it's done. The color here represents the heating stage that the slab is in. After all of this, after the modeling was done, verification was done to make sure that the model logic is accurately representing the constraints we expressed. A number of criteria were checked and confirmed to be correct. The cranes were ensured to be prioritizing the correct tasks and not colliding with each other. It was made sure that the charging and stacking of slabs was done in the correct sequence along with a number of constraint checks. After gaining confidence in the model's ability to reflect its inputs correctly, we moved to the validation, where we made sure that uh, it the model was an adequate representation of the historical performance. Factors such as equipment utilization and time usage model were validated for the cranes and the cutter equipments, and cycle times at the furnace and rolling mill were also cycle times and throughputs were also validated against the historical actuals. This ensured that we were operating at the correct rate and with the correct operating hours. Validation process also helped BlueScope gain confidence in the model and run future scenarios with this. And with this, I would like to hand over to Stephen to talk about how BlueScope was able to use the model outcomes and how it benefited them. Stephen? Stephen, you're on mute.
Sorry. Yeah. So while we're on this side, I'd just like to say how valuable this last step of verification and validation was, and also not necessarily easy. We are, as my role in the project, I deal with both. Been dealing as a bridge between the plate mill operations, which are going to be the benefits of this overall outcome of the project, and also with a wonderful team in the slab yard, and between the two of them, they provided a huge amount of data. And the work that SimWell has done to collate and break down that data, and then do direct comparisons from out of their model to show this validation, build a huge amount of confidence in the work that we've done and the results. So as we move into those results and the outcomes in the next slide, so yeah, to give away the ending, we have gone ahead obviously with our project. You can see here on the right where we're currently at in the excavation phase, soon to be pouring large amounts of concrete for our foundations and our basement. Some of the most valuable part of that was we knew the construction period itself would be the most difficult to manage from a safety as well as a process and being able to supply slabs into our plate mill. They built confidence that the slab yard process as it was would be able to keep up with single furnace operations. While when we run dual furnace, our demand for slab increases at about a rate of 30% increase. And we were able to show that preemptively that with the extra travel time to go around that construction zone, that it would be very challenging to the point of which it would be very disruptive to our rolling process for potential delays. So that enabled us to provide advice to the business around the best way to proceed during this time. Fortunately, or quite unfortunately, perhaps, our order book has been low, so single furnace operation has been sufficient to keep up with all our customer demands. So we adopted the advice around that for our construction period. As we look forward into the future, on our next slide, we were able to show that post-construction, when we were able to reclaim some of the yard, and we established the rate that was required for the new furnace, that there were definitely some challenges that needed to be overcome. The value of this process, we could actually put a size of those challenges, what type of delays might occur, and to be able to work with SimWell to introduce at the later stage of the process some novel solutions, some changes primarily to layout, to create more inventory space in critical locations, and to work with our slab yard to see what was realistic, and we were able to actually come up with some solutions that were well within our contingency. In fact, from a contingency of multiple tens of millions, we were able to come up with two key items that were together sub $1 million to implement on top of our existing budget. So the value, this process value SimWell partnering us to deliver on for our project, to ensure that the business continue to have confidence in the value of our project, and to ensure that the future operations would be stable and able to deliver for our growing market was huge. Some of the key things were around the crane utilization, and speeds of which, and any potential delays that could be occurred in the furnace. So it was fantastic. I'd like to thank SimWell for all their help. Cool. And
Thanks, and
think,
thanks everyone
yep,
for listening.